All right, then, let's get started. So the first thing is recall how to communicate. So this just goes over the definitions of what exactly we're dealing with here. So whenever we're communicating, we're usually trying to get the answer for some function f. And f takes in two strings, x and y. And both x and y are n-bit strings, and f returns some answer, true or false, 1 or 0, yes or no, that kind of deal, our like binary decision function. So the reason this is communication complexity is because you're communicating across two parties. So this is n bits and this is n bits, but this is owned by Alice and this is owned by Bob. So we have to somehow get the answer to this function f, even though we don't necessarily have x and y in the same place. And the function that we're dealing with is usually something like, are x and y equal? Is there some odd? Do they have a majority of ones between their bit strings? So something like that. So we've got Alice, we've got Bob,
And is there an
and we're
intuitive reason
communicating.
that they would always both be length n, not like one be longer than the other?
So yeah, one could be longer than the other. You can imagine a lot of real life situations where that's possible. But for like the intro complexity stuff we're analyzing, for simplicity, it's a lot easier when they're
Okay.
both the same length. And that also lets us analyze things like matrices that we're going to see later that are of square dimension when they have the same length. And if they're not, you can always pad one with zeros. So it's just easier to do it that way. So then the next thing we've got is this protocol, which is basically the list of instructions of how and when they should be communicating in order to get the answer to the function. So the protocol might be like, okay, Alice sends over some random prime she picked and like X mod that prime, and then Bob sends over like the first bit of Y. I have no idea what function they're calculating with this information, but then Alice sends over something, and then Bob sends over something. And at the very end of the day, they should both have the answer to whatever function they're trying to solve here. And all of this right here is the protocol transcript. And it makes sense that we want this protocol transcript to be as small as possible. The less work that they're doing sending things back and forth to each other, the more efficient this function is. So let's give ourselves some notation for the size of the protocol transcript. So we're going to denote the protocol transcript by pi p. So pi is the transcript for the protocol p. And that's going to be how much information that they're like, how many bits they're sending back and forth through each other. So the size of that transcript across all of the inputs, so you have to take the max over all the inputs because it's like a worst case, that's going to be the cost of our protocol. So now we have a cost for each protocol, which solves a function, but we also want to determine what the communication complexity of the function itself is. Because there's lots of different protocols that you could use for the same function, but we need some way of kind of determining how hard this function itself is in general. So we find the cost over all possible protocols for that function. We take the minimum one. What's the best protocol for this function? And that becomes the deterministic communication complexity of that function f. Cool. Any questions on these definitions so far? All right, so then the next step might be to like, how do we bound what the deterministic communication complexity of this function f is? Like what some things that can help us bound it? So the next thing we define is this matrix mf, which you can kind of think of like the answer key of the function. So in this case, if n equals 3, then the strings that Alice could have are these 2 to the 3 or 8 different strings. And these are the same strings that Bob could have. And the function you're computing, let's say if I was computing the equality function, then this matrix would have all ones across the diagonal and everything else would be 0. If I was computing like the greater than function, then I would have ones wherever Alice's string has a greater numerical value than Bob. So basically this matrix f is like the answer key. If you had this matrix, it's like a lookup table of what your function f is. On this matrix, we define this notion of a rectangle, which is like slightly different from what you're probably imagining of like a contiguous block rectangle. So we define the notion of a rectangle as a submatrix where you take a subset S from the strings that Alice could have. So let me just like pick a subset. Like I pick this one and this one and this one. That's a subset of the strings that Alice could have. And then I pick a subset T of the strings that Bob could have. And from here, I define a rectangle. So basically, what are the entries they coincide on? Would be all of these entries. So this is the rectangle I just defined. So things to note is that it doesn't have to be contiguous, and like, even though it doesn't have to be contiguous, it does have some nice properties. Like I can't have a rectangle that consists of like this square and this square without also consisting of the remaining things, so that it like has 4 corners. So it's not just a random subset of the entries in the matrix, but it's also doesn't have to be a contiguous subset. One thing just to keep in mind for like to picture it is that the order of the rows and columns in this matrix, they don't have to be in numerical order. So we could technically like take all these little green pieces and squeeze them up into the corner and actually make it look like a rectangle. And the nice thing about an iPad is that I can actually do that. I'm going to take these and kind of reorder them. So all of these are going to be first, and let's scooch everyone else down. So my set S is first, and I'm going to do the same thing with T, where let's move all of our selected entries to the start, move everything down. And that moves our entire rectangle up. And now it's like one contiguous block. So you should keep in mind that the order doesn't matter, but that doesn't necessarily mean that your rectangle has to be contiguous. It was still a rectangle before. So that's the definition of a rectangle. The next thing we want to talk about is a monochromatic rectangle, which is pretty simple. It just means that all of the entries in this rectangle are the same value. They're all zeros or they're all ones. And then we define, I guess not define, we have this theorem, which honestly I think is pretty important. It should be its own bullet point, which just says that if you have a protocol P that computes a function, and the cost of that protocol is C bits of communication, then C induces a partition of F into at most 2 to the C monochromatic rectangles. So let's break that down. What we're basically saying is like, okay, let's pretend that this green rectangle right here is a monochromatic rectangle, and I've got some protocol P that that requires 2 bits of communication. Well, then 2 to the C is 4. So that means I should be able to partition this matrix into 4 monochromatic rectangles or less. So a partition might look something like this is one rectangle. It doesn't have to be contiguous, but it's easier to draw that way. And then like this is one other rectangle. So I could partition it into 4 or less. So in this case, 3. And just to see it out one more time, the cost of some protocol equals C implies, and this is a protocol that solves the function f, means that you can partition mf into less than or equal to 2 to the C monochromatic rectangles. Okay, are there any questions on this? Because I know that's a lot to like take in all these different definitions for rectangles. Hopefully some of these definitions are giving you ideas of things we might use to analyze these rectangles and this matrix in general. The idea of the columns order not really mattering that much, but the values in them mattering, hopefully that rings a bell of something like the rank of a matrix. If not, don't worry, we're going to review that. Any questions so far? Cool, so let's get going. I just copied down this from the last slide, and let's denote CDF. That's going to be the minimum number of rectangles that you need to create a monochromatic partition of the matrix MF. So a corollary to this thing highlighted in yellow is that the deterministic complexity of some function f has to be greater than or equal to the ceiling of the log of the minimum number of rectangles that you could partition it into. So the proof for this is actually pretty short. It directly follows from this theorem. So at the very end, if we have time, we can come back and prove it. But for now, we can kind of take it as a theorem to use, that there's this nice relationship between the complexity of the function and the cover of like the minimum size number of rectangles you would need to cover the matrix. So having this relationship, you can already kind of see that if I want to try and figure out like how difficult it is to compute this function, it kind of helps to know a lot about the matrix of that function. So to see an example of that in action, here's a function we definitely know the matrix of. So the equality function, its matrix looks like this with a bunch of ones on the diagonal. And we have this bound on the complexity of the function based on how many rectangles you can partition it into. For the equality function matrix in particular, it's really easy to see how many rectangles you can partition it into because of the fact that all the ones are on the diagonal. Because they're on the diagonal, they have to be each on their own square. If they are not own square, own rectangle. If they weren't, like if you somehow decided, you know what, I want this one and this one to be in the same rectangle, well, that would mean you also have to include the corners of that rectangle and include these zeros, and that's not monochromatic at all. And another important thing to realize is that this holds because of these like linearly independent columns of the equality matrix. So even if I like went ahead and switched the order of these columns, like if I just took this column and put it there and put this column and put it there, the same property still holds. It doesn't have to be on this diagonal or anything. It's just the fact that each one of these ones kind of exists in its own separate row, that you need each one of them to be on their own separate monochromatic rectangle. So because of that, we know that the minimum number of rectangles, this CDF, that minimum number of rectangles can't be smaller than 2 to the n. And because 2 to the n is the size of this, how many rows or how many columns we have. So from there, we can get that the deterministic complexity of the equality function is going to be greater than or equal to the ceiling of the log of how many monochromatic rectangles you can split it up to, which we saw was 2 to the n. And this is n plus 1, which is what we wanted to show. But of course, in general, it's not actually that easy to figure out what this CDF is going to be.
Don't we need the plus 1 inside the log as well? Because the ceiling of the log of 2 to the n is just n.
Then
I think what I
might
got
have
in
missed the
lecture
plus 1.
is
Yeah,
we said there has to be at
one.
least one rectangle for all of the like
oh yeah, because the zeros, yeah,
all of the zeros.
There is a plus 1. Yeah.
We should need 2 to the n of those as well, I think.
Exactly.
But, yeah.
We need 2 to the n for all the ones, but then the plus 1 is because we also need a rectangle for the zeros, at least one for the zeros. Good catch. Yeah, that's where this plus 1 is coming from. The second thing is that, it's not that easy to determine what like the minimum rectangle cover for a matrix is. So we have a bunch of strategies to try and figure out what it is, some heuristics. One thing we're going to use a lot is to bound by the rank, and we'll see that in a later problem. So it's a helpful bound if you know the minimum rectangle cover, but that itself is also kind of hard to find. All right, so with all those definitions in our bag, let's go ahead and move on to our first problem. So this is pretty interesting, and again highlights the fact that communication complexity relates to so many different things. We're going to prove a language is irregular using communication complexity topics. So we define this language, WW. So in other words, the same string repeated twice, one after the other. And we know that this language is irregular if you did like the pigeonhole principal argument from before. But now we're going to try and prove that it's irregular using communication complexity. So we just saw that the deterministic complexity of equality is greater than or equal to n plus 1. And now we're going to get a contradiction by saying, well, we want to show that if L is a regular language, that's going to imply that the deterministic complexity of equality, instead of being at least n plus 1, is going to be constant time. All right, so let's think about how we might set this up. We know L is regular, so we've got some DFA, we already kind of used D, so some DFA A for automata that decides L. And now we want to set this up in terms of Alice and Bob solving this equality problem using the fact that they both have access to this DFA A. So we've got Alice and we've got Bob. Let's just make some boundaries. So this is like their communication boundary. Alice has got X, Bob has got Y. And just to make it more explicit, they both have access to this DFA A. And we want to try and figure out like how they're sharing things with each other. Using this automata A, it should be possible for them to figure out whether their strings are equal, sharing a constant amount of information. Any ideas?
We can exploit this fact that we have a like fixed finite number of states in the automata. And basically like it's WW, so we have like we have X and Y, and it's in the language if X and Y are the same, if we just append them together, and it's not in the language if X and Y are different in some location. So we just have like Alice or Bob run the automata on X, let's say, if Alice does it, and then send like which state it is, which should take like log of the total number of states, which is some constant bits of information to send over. And then we just like finish the computation on Bob's side.
Exactly. So you pointed out the two key ideas here. One is that, well, our language is really conveniently set up to find if two strings are equal, just stick them together and run it on the DFA, and you can figure out if those two strings are equal. And then the second idea is that, well, we don't actually want to concatenate X and Y together and plug them into the DFA, because that would imply that either Alice or Bob has both X and Y, in which case we would have had to send over all of the n bits over to one of them. So we should split up the computation. So just to walk through what you said, Alice can simulate the DFA on her input, and that simulation is going to stop at some state, Q, and it takes a constant number of bits to send over what Q is, like what that state is. And now Bob can simulate A of Y starting at state Q, so like basically where Alice left off. And whatever the answer is, accept, reject, 0 or 1, it takes 1 bit to send over whatever the answer was back to Alice, and they both have the answer now. And we just decided the equality function in a constant, because this takes a constant amount, this is just 1 bit, in a constant number of bits. Cool. Any questions about that? All right. So let's move on to the next question. This one's a little bit more involved. We're going to show, like kind of hinting at it from before, that the deterministic complexity of a particular function is somehow related to the rank of the matrix. We're going to show explicitly that the deterministic complexity of some function f is greater than or equal to the log of the rank of the matrix of that function. And just as a reminder, if you don't remember 241, because I didn't either, the rank of a matrix is going to be the maximum number of linearly independent column vectors in the matrix. So if you have a matrix where every single column is the same, that trivially just has like one linearly independent column. If they're not all the same, then you might have to do a little bit more analysis on like whether they are linearly independent or not. But also remember that our matrix, all the matrices we're dealing with for M sub f, they're all consist of zeros and ones. So you don't have to worry about like 001 is technically not linearly independent from 002. In our case, it's easy to analyze because they're all zeros and ones. And another property we're going to be using is the fact that rank is subadditive. So in other words, the rank of the sum of matrices is always going to be less than or equal to the sum of the rank of those matrices. So this is a pretty useful property. In other words, if you want to bound the rank of some matrix, if you found a way to split up that matrix into the sum of other matrices, and those other matrices were easier to find the rank of, then you would be able to find the rank of the original matrix, or a bound on the rank of it. And of course, we have this highlighted theorem from before, which will be useful to us. So this problem is definitely a bit more involved, so let's just step through it. So the first thing to notice is if we just first apply this theorem, we know we've got like the best protocol, P for our function f. By definition, its cost is going to be the deterministic complexity of our function f. And just applying the theorem, that means that we can partition MF into, I'm going to give it an explicit number. We know it's less than or equal to 2 to the cost. So let's say that number is like R rectangles. Or I should say explicitly, R monochromatic rectangles, such that R is less than or equal to 2 to our cost, which was the complexity of F. All right, so we've got that fact under our belt. Somehow we've got to use that to get a bound on the rank of our matrix so that later on we can take the log of that rank and compare it. So if we've got R monochromatic rectangles, let's make this more explicit. So remember, we define each monochromatic rectangle by like what subset of the strings of the X strings and what subset of the Y strings we're choosing. So we can define each rectangle as like S1 cross T1, S2 cross T2. And we've got R of these, so SR cross TR. So using these monochromatic rectangles, my goal now is going to be, how can I split up my matrix MF, which is this, into the sum of a bunch of other matrices so that I can bound the rank. So somehow if I could add up these monochromatic rectangles and get my original matrix M, that would be really useful. But the dimensions of all these monochromatic rectangles are kind of not the same at all. Each rectangle could have a different size, and they aren't really like a contiguous matrix. They've got gaps in between them. So in order to add them, we're going to define these like submatrices that are defined based off of our rectangle. So basically all they're going to be is that if you take a rectangle, instead of just looking at the rectangle, look at the entire matrix, but set all of the numbers that are not in the rectangle to 0. So visually, just to see that, here's an example of what that would look like. So if this black rectangle right here, that is my matrix MF, I pick some rectangle, let's say it was like S3 cross T3, for example. My rectangle is going to be some subset of the entries here. And they are monochromatic. So in this case, I guess I should have drawn them all of the same because it's monochromatic. Oops. Let me fix that real quick. Since it's monochromatic, we know all of these have the same value. So let's say they're all 1s. Make them 1s here. All I'm going to do is take that monochromatic rectangle, so this like pink rectangle I have here, and that was bothering me. And I'm just going to pad like the rest of the matrix with zeros to create another matrix. Let's call it M3 because it was formed from the monochromatic rectangle 3. So let's define these new matrices. So for each monochromatic rectangle, we're defining a matrix. So we've got our little matrices. This process that we're doing where we just kind of take the monochromatic rectangle, except everything else turns into zeros, you can more explicitly define that by saying, okay, the XY entry of the new matrix we're defining is just going to be the original matrix entry if we're in this rectangle. And otherwise it's 0. That's just the formal way of writing down what this process was. Hopefully now it's pretty clear that because these monochromatic rectangles partition our original matrix F, if you add up each of these monochromatic rectangles, you'll end up with the original matrix. So you can kind of imagine if this is M3, and then M2 consists of some other partition, and M1 was this, and M4 was this section. If you add all of them together, because they partition our original matrix, they add up to the original matrix. And now we can just use our subadditive rank property by saying, well, if our original matrix is the sum of all these little mini matrices we made, and there's R of these, well, that means the rank of our matrix is going to be less than or equal to the sum of the ranks of all of these matrices. And by the special way that we define each of these M sub I, what do we notice about the rank of these matrices? to be less than or equal to r, which is less than or equal to 2 to the deterministic complexity of f. And just taking the log on both sides, we have log of the rank of our matrix is less than or equal to the deterministic complexity of f, which is what we wanted to show. So that's applying a bunch of pretty interesting properties. So we've got this lower bound on the deterministic complexity of our function based on the log of the rank. An open question is whether there's also an upper bound. So is there some way, we don't know if this is true, to bound the log to some power k of the rank of the matrix? So this is like an open question. But it's interesting. We have this lower bound, and that can help us with the deterministic complexity of some function. All right, so the last question is a zero knowledge proof kind of question. So let's walk through what it's asking first. The problem of telling whether y in z star n is a square, i.e. if it's equal to x squared for some other x in z star n. So that's considered to be a hard problem for the form n is equal to pq for two large primes, p and q equivalent to 3 mod 4 when one does not know the factorization of n. So I'm not quite sure of the proof of this, but we're just going to take it for granted that this is a hard problem. So if it's a hard problem, if Ada happens to know that y is a square, then we're like, wow, that is like some big brain move. He must have done a lot of computations or must have worked really hard to figure out why y is a square. But of course, he might be lying. Maybe he's just trying to get some clout, be like, I know that the y is square. So how can we really tell that he's telling the truth if he doesn't want to give us the x? So in other words, we know that if y is a square, then x times x is y, but he doesn't want to give away, you know, like his secret sauce of what x he used to show that y is a square. But he still wants to convince us, or in this case, like convince Vipul, that y actually is a square. So how can we do this under like the idea of what a zero knowledge interactive proof is? So the rules of the zero knowledge interactive proof are that if Ada is telling the truth and y actually is a square, then he should be able to convince Vipul with probability 1 using whatever protocol we design now. And at the same time, Vipul shouldn't learn what x is. He shouldn't be able to figure out what the square root of y is. On the other hand, if he is lying, we give ourselves a little bit more leeway here because we can't make like a perfect protocol. If he's lying and y isn't a square, then with probability at least 1/2, Vipul should be able to catch his lie. And remember, this is useful because we can always boost this up to however much we want. So as long as we can get the probability at least 1/2, we're pretty good. So some first ideas we should notice right off the bat are because we can't share x itself, but we do have to send over some information to Vipul so he can kind of check something and check that Ada isn't lying. One useful strategy there is to multiply x by some random element of z star n. And if we ever sent that over, well, now we've kind of sent him over x, but he can't extract x from that random thing. So in other words, it might be useful to pick a random element z from z star n. And later somehow if Ada sends over x times that z, we know that Vipul won't be able to extract the original x out of it. Okay, but if he sent over a random x times z, well, just because Vipul can't extract x out of it, he still needs to somehow confirm that that x really is the square root of y. So in order to help him out with that, we also kind of need to know what the square of this z value is so that when he squares it, he would actually be able to see y. To make this more explicit, let's say a is equal to z squared. And of course, everything here is going to be taken mod n. So what does that look like? Let's make this a lot more explicit. So Ada is going to give Vipul whatever this square of z is. Because if Ada sends over x times z, then the square would be useful for confirming that x really is the square root. But remember, at any point in time, Ada could be lying, including the protocol itself. So we're designing a protocol, assuming right now that Ada really knows that y is a square and he has the value x. But our protocol should work even if Ada decides to completely lie and break this protocol. So to ensure it works regardless, we need to check both that the xz, like we were saying before, but we also need to check this itself. Like maybe right now, Ada already broke the protocol and he didn't pick a random z and didn't send over the square of that z. He sent over some like sneaky thing that actually helps him later on. So this is also something that Vipul would want to check. So one way he can check it is he flips a coin and sends over that coin flip result to Ada. So that coin flip result is either going to be heads or tails, and depending on that, Vipul is going to check something else. So if the coin flip result was heads, then, so in both cases, Ada is sending over like some number C back. So only one of these red arrows happens. He's sending over some number C. In the case that it's heads, Vipul is going to check that Ada actually like followed this part of the protocol. In other words, this part of the protocol is basically saying that Ada knows what the square root of A is, because if he followed the protocol, it should just be whatever he chose randomly Z to be. So in this case, Vipul is going to ask that Ada send over Z, because that would mean that he knows what the square root of A is. And it's really easy for Vipul to check that, because he can just go ahead and check that C squared is equivalent mod n to the A, which he was already sent from the first step. And in the case that it's tails, we're going to do that idea of sending over x, but multiplying x by that random number so that you're kind of hiding the value of x. So in the case that it's tails, send over x times c, in which case Vipul can check that c squared in this case is now going to be equivalent to y times a. So let's actually walk through and make sure that this claim works. So if Ada is telling the truth, then Vipul should be able to confirm 100%. Well, let's walk through this. If we're Ada and we know for sure that y is a square, and we've got the x that proves that y is a square, then we can just follow the protocol. We pick some random number, we square that random number, we send over the square to Vipul, he flips a coin. In both the heads case and the tails case, we're covered. In the heads case, we just say, well, here is the square root of that number A I sent over. I know what the square root is because by definition, it was the square of that number I picked. And I can just send that over, all set. And in the case that it's tails, well, I kind of do the same thing. I know what the square of that number is, it's C, and I can send over my original X, and I don't have to worry about you being able to find that X because I've multiplied it by a random number. So now it's like, it's randomly distributed across Z star n. You won't be able to extract the X out of there. And I send that over, and you can check the square root of that. Okay, so 100%, both sides would have to be convinced. There's no reason for Ada to lie. Now, in the case that he is lying, so he said y is a square, but he doesn't actually know the x that makes y, that proves that y is a square, that x times x is equal to y. Well, in that case, if he follows the protocol and actually picks a equal to z squared, where z squared is some random element of z star n, well, in the heads case, he's fine, because, yeah, he can just give the square. But in the tails case, he's kind of screwed, because, what is this x going to be? He would have to, make it up, in which case, when Vipul checks, he's caught in his lie. So in the tails case, maybe he can design his a to be something such that, the square root of a, when you multiply it, you get ya out of here. But the claim is that if he maliciously picked his A and he didn't follow protocol, he didn't pick some random thing up here. If he decided to pick his A in such a way that the Z that would work out would end up making this check succeed, this check must fail. So in other words, 1/2, with probability 1/2, Vipul always catches him in his lie. To make that more explicit, what we're trying to show is that if Ada is lying, either he doesn't know the square root of A, or he doesn't know the square root of YA. In other words, one of these has got to fail. The contrapositive of that is if he knows both the square root of a and he knows the square root of ya, well, then he shouldn't need to lie because that would mean he knows the square root of y itself. And if he knew the square root of y itself, he knows the x, he wouldn't need to lie, he would just follow the protocol. To see that explicitly, it's like if he knew the square root of a, so in other words, if he knew the square root of a, and he knew the square root of ya, well then y is just going to be equal to, well, I guess I should break it up into steps. Then we know, just plugging in what we have for a, we know this. And since these are taken from z star n, so we know their GCD is all equal to 1, that they've all got inverses, well then y is just equal to this, in which case he already knows what the square root of y is. It's just going to be, he can find out that x is this. And if he knew what the x was, then there's no reason for him to lie. So he would have only lied if he was missing, if he didn't know this one or he didn't know this one, in which case Vipul can catch his lie with probability 1/2. Cool. So are there any questions on this one? All right. So we are actually pretty good on time. So we can go back and prove that little corollary from before if we want to do that. So going back, so that was this one. So the proof of this one was basically we want to just use this theorem and apply it so that we get this property. So we know that if we've got some protocol with some cost c, that we can partition our rectangle into less than or equal to 2 to the c monochromatic rectangles. So we know that there's some best protocol with cost df, which means we can partition, just pretend I know how to spell, can partition mf into less than or equal to 2 to that cost, which is df, rectangles. And if we can partition it into less than or equal to 2 to the df rectangles, well, we know that this is definitely less than or equal to the minimum number of rectangles because it's just some partition. Any partition is going to be greater than or equal to the minimum number. And then we can just take the log on both sides. Yeah. So that just is what gives us a nice connection between the complexity and the minimum rectangle cover. Cool. So that was all the problems I have for you guys today.